All right, so the okay, I want to do an example here because all the problems they did on the homework last night, when you put the number next to moles and kilojoules, it was a 1 next to moles and kilojoules. But it's not always a 1 with moles and kilojoules. That's why I'm going to do this example. Okay, so here's a chemical reaction. If 15 grams of C2H4O burned, how much energy will be released? And what I'm trying to counteract is every time you did on the homework, this was a 1. And it's not always a 1. So that's why we're doing this example. The math's not any different. It's just that that 2 is not a 1. Which is going to affect our answer just a little bit. Eraser doesn't want to work. There we go. Hey. So I start off with the 15 grams of C2H4O. I want to get rid of grams of C2H4O. What can I turn grams of C2H4O into? Well, I don't want to talk about C2H4O anymore, so I need to get to moles so I can talk about something else. So I need to go from grams to moles so I can talk about something else on the next one. So 44.06. How did I do that? Because we just did 46.08 when it had 2 more H's. So I just took off 2 of the H's. Okay. And that's 1 mole, because when I take the numbers off the periodic table, it's for 1 mole. Now, I want to get rid of moles of C2H4O and change it into energy, kilojoules, and I get those numbers right out of the equation. So the number in front of kilojoules is 790. The number in front of moles of C2H4O is a 2. Because it says 2 in front of C2H4O. And those units have canceled out. So I'm left with just kilojoules, so I'm ready to push buttons. 15 divided by 44.06 times 790 divided by 2 equals 130 or 134, depends on where you round it. Since this only has 2 digits, I tend to write it as 130. I round it off to about as many as I started off with. Your calculator is going to say 134, and the units are kilojoules. So the only thing different is this was not a 1 because this was not a 1. Are we okay with that? Hugely different from how we've been spending our last 3 weeks in terms of math. Okay. And that's the beauty of it, is we don't have to learn new math if we learn conversion factors. We can do the same math over and over again and apply it to different problems. Okay, so which direction? Well, exothermic reactions release heat. Because that's the definition of an exothermic reaction, is one that releases heat. So when I put it in the equation, I need to put it where I put things that are given off by the reaction. I need to put it on the product side of the equation. I'm going to make heat, and the things I make are on the right-hand side of the equation. So I can tell that this is exothermic because the heat is written over here. Ta-da. because right-hand side are the things you make. I'm going to start off with NH3 and O2. When I'm done, I'm going to have H2O, NO, and I'm going to get heat out of it. And the coefficients and the numbers tell me how much in moles or kilojoules. Can everybody guess what the next line is going to say? I just did exo, so I'm going to do endothermic. What endothermic reactions? What's it going to say after that? What do they do with heat? They absorb it, not release it. So heat will be a reactant. The heat goes the opposite direction. You write it on the opposite side of the arrow. So I can tell this is endothermic because the heat, the kilojoule part, is on the reactant, the left-hand side of the arrow. So this second reaction requires heat. I got to put heat in. So in the past on those, we said you could write the word heat on top of the arrow. Well, heat on top of the arrow means I have to put the heat in. It's endothermic, but it doesn't give me the number that the 4490 kilojoules gives me. Okay. We also said that instead of writing the word heat, you could put a triangle on top of the arrow. Not a triangle, it's the Greek letter delta. Why a triangle? Because they're just too short, they're trying to shorten delta H, that change in enthalpy. Right? That the heat is really how much the heat content changed. So that delta is the delta for delta H. And that's why I put delta there. But you need a number if you really want to figure out how much. The delta just tells me I have to put heat in. If I want to know how much, I got to write how much in. Okay, so how is that delta H going to tell me direction? Because that heat in a thermochemical equation, that thing you write in, is the same as the change in enthalpy. The reason why you get heat out is because the heat content changes. The reason why you put heat in is because you need the heat content to change in order for that to happen. So we have two different ways of talking about the heat. We can put the heat right in the thermochemical equation, or we can talk about the delta H separately. The change in enthalpy we can talk about separately. So instead of writing, if I want to put it in there, if I want to talk about delta H instead of writing it in, I just write delta H off to the side after you've written the equation. So I'll write the whole equation, I'll stop, leave a space, and write delta H equals. But when I go to write delta H, I need a direction for it. I need, when I write delta H, to say whether it's endo or exothermic. So, exothermic. Exothermic reactions release energy, right? So they start with, so remember our graph, they start with lots of energy, they end up with less energy. What kind of change is that? Positive change or negative change? That's a negative change. So if it's exothermic, delta H, when I write it, I'm going to put a negative sign in front of me. That's all that negative sign is telling me. Well, it's not that's all. That's what that negative sign is telling me. It's telling me whether I got to put the heat in, or I'm not going to have to put the heat in, that this is going to burn my fingers if I try to pick it up. You're just going to make heat come out. So that all day yesterday, we wrote this equation and worked with it. Another way of writing exactly the same thing is to write that. So I wrote the whole equation both times. And because it was exothermic, I wrote if I put the heat in, it goes there. If I write it off separately, delta H equals, it's the same number. I just have to decide on the sign. And because it was negative, or because it was exothermic, it's negative. A negative change in heat means that it released heat, because that heat had to go to someplace. So these are just two ways of writing exactly the same thing. Okay. So if exothermic delta H is negative, so if endothermic delta H is positive. Surprise, surprise. So here's an example of an endothermic reaction. I can tell it's endothermic because of where the energy is written. The energy is written before the arrow. The energy is a reactant. I'm going to have to put the energy in to make this happen. If I don't put S2Cl2 in this, if I don't put S2Cl2 in, it doesn't happen. If I don't put CCl4 in, it doesn't happen. If I don't put those 112 kilojoules in, it doesn't happen. So you can almost think of heat as like a limiting reagent sometimes. If you don't put it in, nothing happens. So to present exactly the same information, I could have written this. I write the whole equation out, and then off to the side I write delta H equals 112 kilojoules. But this time, delta H was the heat was a reactant. It was on the reactant side. It was endothermic, so delta H is a positive number. That's all there is to it. Ta-da.